So we're looking at problems in Chapter 8-1. We're going to look at how to develop confidence interval when we know the population standard deviation sigma. Problem 47, page 363. A random sample of 11 Samsung Galaxy smartphones being sold over the internet in 2013 had the following prices in dollars. Assume the population standard deviation is 85. The minimum value is 35, and the maximum value, it looks like in the data set, is 385. The first question asks, explain why it's necessary to check whether the population is approximately normal before constructing a confidence interval. Well, in order for us to use the sampling distribution for normality, we have to realize that under the central limit theorem, n has to be greater than 30. In this particular case, n is less than 30. So we have to check for outliers or skewing effects. So to do that, we can do it two different ways. One is to check for box plots. And in this case, we're going to do that. The other way is to calculate a skew measure, which we can do on Excel. So in this particular case, we enter the data into L1. We hit second y equals to get to the plot information. We hit plot 1. We turn on plot 1. We choose the box plot with outliers. We make sure that the X list is L1, the frequency is 1, and the mark is a little box. The next step is to set up our graph window. So we'll have an X minimum of about 100 and our X max to be about 500. Our X scale will be 20, and then the Y min value is 0. We will leave the Y max value at 10. When we hit graph, we end up with a box plot that looks pretty good. It's symmetric and there are no outliers. So it looks like this data set is approximately normal. So the next step is, in part C, is to construct a 95% confidence interval for the mean price of Samsung Galaxy phones sold on the internet in 2013. Well, first of all, I'm going to do it by the calculator. If we hit the stats key and we move over to the test icon and hit enter, we will select option 7, which is the Z interval. Since we've entered the data into the calculator, we will choose the data option rather than the stats option. For sigma, we will enter in 85. Why? Because we have a standard population of 85. Our data is in L1, frequency is 1, and our sea level is 0.95. We will hit calculate, and when we hit calculate, we get the following screen where this is where our confidence interval is. It has a low value of 202.59 and 303.05. So our interpretation is that the average price of Galaxy phones is between $202.59 and $303.05 based upon this particular sample. And we are 95% confident of that estimate. If we're doing this by hand, the first step is to find the point estimate. Well, in this case, the point estimate is equal to $252.82. And the next step is to find my margin of error, which I'm going to call M. So M in this case is equal to Z times sigma divided by the square root of n. Well, to know what Z is, we have to look at our level of confidence. And we go to the bottom of page A3 in the appendix, back in the back of the book, and that's on page A8. And we find a Z value for 95% to be 1.96. And we know in this case what sigma is. Sigma is 85. And we have 11 prices. So our prices is 11 here. When we do our calculation, we get $50.23. So now we have a point estimate and we have a margin of error. Now we can calculate our 95% confidence interval. So we have a lower bound is equal to x minus m. So this is our lower bound, so it's 252.82 minus 50.23, and this is going to be 202.59. And then we have an upper bound of our confidence interval, which is x bar plus mu, which is equal to 252.82 plus 50.23, which is equal to 303.05. So these two values, our upper and lower bound, matches with what we got on the calculator. So now we're looking at problem 51 on page 364. Here we do not have a data set. Instead we have numerical information, some statistics. In a simple random sample of 100 electronic components produced by a certain method, the mean time was 125 hours. Assume that the component lifetimes are normally distributed with a population standard deviation of 20. Right? So the first thing we're going to do is look at the calculator. Again, I hit the stats key, I move over to test. I select option 7, which is my Z interval. And I choose stat this time because I don't have a data set. I enter in 20 for my population standard deviation. I enter in for the mean value of the components of 125. I enter in the sample size n, which is 100. And I put in my C level of 0.98. I hit calculate. How easy is this? And we get a Z interval of a low bound of 120.35 and an upper bound of 129.65. So again, if we're doing this by hand, the first step is to find the point estimate. And our point estimate, right, is x bar is equal to 125 hours, right? Our second idea is to find our margin of error. Our margin of error, which is Z, times sigma divided by the square root of n. Now I look up my z value under the table of A3, and I find that that value is 2.326, and I'm going to multiply it by 20 divided by the square root of 100. So m is equal to, when we did the let's see, I think it's 4.652. Now, we want to calculate our 98% confidence interval. So, we have a lower bound is equal to x bar minus our margin of error, right, which is equal to 125 minus 4.625, and if we round up to 2 decimal places, we end up getting 120.35. And for our upper bound, we have x bar minus m is equal to 125 plus 4.625, and we get 129.65. So that's our upper bound. So in this particular case, the average lifetime of components, or the mean time of components, for these type of electronic components is between 120.35 hours to 129.65 hours, and we are 98% confident on that estimate. So the last thing we want to talk about is how to calculate the sample size when we know the margin of error with a 99% confidence interval. So usually researchers will begin their study by starting out with the margin of error that they're willing to live with and the level of confidence they would want in their estimate. So in class we discussed the formula, which is n is equal to z squared times sigma squared divided by the margin of error squared. In this case, we look up the 99% confidence interval information for z. We get a z value in this particular case of 2.576. We square that. We multiply it by 20, which is our population standard deviation squared. And then we divide this by our margin of error squared. And we get a value of 294.92. And we always round up, so we get an answer of 295. So we need a sample size of 295 to get a margin of error of about 3 hours for a 99% confidence interval. Well, that concludes our problems in Chapter 8-1.